Hi everyone. So today we're going to talk about fields, and this is something that we've seen before and that we should at least vaguely understand. But we're going to be doing this in a different way. So first we talked about gravitational fields and then we talked about electric fields. Today we're just going to do both at once because actually they're very similar and there's lots of properties that they have that are exactly the same. So if you understand the electric field very well, then you automatically understand the gravitational field very well. So you may remember that a field is just something that a charge produces, right? So if I have this test charge, let's say here, and remember that a test charge is a charge that can feel the effect of a field but cannot modify that field at all. So here I have my test charge, and I know that this test charge is going to be pushed this way. And then I wonder, well, how does this charge know that there's a positive charge here if it's not touching it, it's not seeing it, doesn't have eyes? And the answer that we normally give is that, well, it's not really seeing this charge, but it's actually seeing the field of this charge. So this charge creates around itself this web-like structure that we call an electric field. And when I put a particle in the electric field, it will instantly feel the repulsion in this case. And we can wonder, okay, but is this a real thing, or are we just imagining things? Is this just a mathematical artifice? But it turns out that fields are actually very real. Now that in quantum mechanics, for example, fields are the only thing that's real. So actually, electrons and positrons are just vibrations in a field. But even if we don't get into quantum mechanics things, if I actually remove this charge is going to still feel the effects of the field for a limited period of time, which means that it's not the charge that does the force, it's the field that does the force, and you can have a field without a charge. So fields are not just mathematics, they're real. They are created by charges or by masses, and they're really there, and they can carry energy, and that's why light waves are just an oscillation of the electromagnetic field, and they can do all sorts of things that we normally associate with things that exist, that are not just mathematical artifacts. Now let's compare. So here I have my electric field, and here I have a mass. And in a mass, we also have a field. It's just that in this case, because it's gravity, it's always attractive, right? So it will look something like this, which would be very similar to what we would have if we had a negative charge on this side. So something like this, and in the same way I could put a test mass here. So here's my test mass, and again a test mass is going to be a mass that can feel the effects of a field but does not modify the field in any meaningful way. So for example, you are a test mass on Earth because for all practical purposes you're not modifying the gravitational field of the Earth at all, but you are feeling its effects. So here I have my test mass, and it's instantly going to feel the effects of the field created by this planet or whatever it is around itself. And then if I remove it, this is still going to feel the effect of a field for a little while, which means that there is a gravitational field being created by this thing. Okay, so now it's time to remember a little bit of the mathematics of fields that we've done before. And these mathematics are what actually describes how strong a field is and the effect that it has on the charges that are around it. So the first thing that I'm going to do is to remind you of the forces that describe the force between electric charges and between masses. Okay, so here I have this little electric charge. Let's just call this big Q. Let's just call this small q. And I'm going to do the same thing for a mass. So I'm going to make this little mass here. I'm going to call it little m, and this one's big M. Because I want you to notice the symmetry between these two things. They're the same thing, or very, very similar. Okay. So first thing, let's see if we recall the formula for getting the electric force between two bodies. Now, we found out that the force had to be proportional to both of the charges, because the more charge, the more force, and that seems like something that makes sense. So Q, Q, and then we found out that of course the more I separate them, the less the force. Actually, the argument that we follow was that here's my charge, and somehow the field is getting more and more, less and less dense, the field lines, right? And they're getting distributed not over a circle, because this is really in 3D, but they're getting distributed over the surface of a sphere. And the surface of a sphere is 4 pi r squared, which means that the further I go, the weaker the field gets, but not proportionally to r, but to r squared, because the field lines are getting distributed over a larger and larger surface that goes with r squared. So here we have r squared. And finally, we need to multiply by a constant simply because nature and us do not use the same units. And this constant was 9 times 10 to the 9, but that's not important now, it's in your data booklet. One thing that's very important to remember is that this r does not mean radius. R always stands for the distance between the centers of the charges. Not between here and here, or between here and here, between the center of this charge and the center of this charge. And we can do this because any spherical charge acts as if all the charge was in the middle. And so does this one. Okay, so this was the formula for Coulomb's attraction between these two guys. Now let's take a look at the gravitational case. Okay, so again we had that the more mass we had, the more force, and then the more mass we had, the more force. So force had to be proportional to both masses. So M, and just like this, the field gets spread out over a larger and larger surface that goes with r squared. So this also has to be inversely proportional to r squared. And then we need a constant to account for the fact that we don't measure in the same units than nature does. So this just allows us to convert between our units and nature's units. Good. And now if you take a look, these two things are just the same. Here we have R2, here we have R2, here we have a constant, here we have another constant, and then we have big Q, small q, big M, small m. So all that changes is that we're replacing charges by masses. So in a way we could say that mass is the charge of the gravitational field. Right? Charges create electric fields and suffer electric fields. Masses create gravitational fields and suffer gravitational fields. So it's really the same thing, we're just changing the letter. So we have two different fields with two different charges, but the equations are the same. So in general we could say that any field, and actually that's not true because of some really complex reasons, but any field that behaves like electricity will always be some constant times charge 1, charge 2 divided by the distance squared. And this happens, this works most of the time. So, okay, so that's force, and that's what we did in standard level, and it's not very useful, because most of the time we don't even know what's in here. We know that there will be some charge, we have no idea which charge, right? We know there's a field. So there's a field going this way, and we want to know how strong the field is, regardless of what I put in here. Now, of course, if I put something that has lots of charge in here, then it will receive more force than something with very little charge. But what's important is, okay, yeah, but how strong is the field at this point? So how much force per unit charge am I going to get? And we call this the electric field. So let's do this. Let's write the formula for that. So I have the force, and I want to know the force per unit charge. So ideally, what I would do is like, okay, well, if a charge Q receives this much force, then the force per unit charge will be just the force divided by the charge. So the electric field is going to be the force divided by the charge, the small charge, because I'm assuming that this one's just there, creating the electric field. And then some really simple math reveals that this Q will get crossed out with this Q. So basically all I get is K Q over R squared. And that's the formula for the electric field. But it's not important, but it is important that we remember that the formula for electric field, but actually what's really important is that we understand what electric field is. it just tells us how much force per unit charge a charge would receive here. If we understand this, then we can derive this. And if we can derive this, then we can derive that. So we need to understand what we mean by a field. It's like, well, at this position, if I put a charge, how much force will it receive, depending on how big that charge is. Okay, so now we do the same for the gravitational field. Well, same case, right? So we want to know how much force per unit of gravitational charge, which is the mass. So in this case, we're going to take it to be this little mass. We could do the other way around, but here again we were assuming this creates the field, this just sees it because it's too small to affect the field in any way. Good. So we're like, again, well, so the gravitational field that we're going to go little g is just the force per unit of gravitational charge, which is the mass. Same thing as this. So as you can see, these things are completely symmetrical. We're just changing q's by m's, but the idea is the same. And then if we do this, we will quickly see that this m and this m will disappear because they will cross out. So then we'll have g m over r squared, which again has exactly the same shape as this thing, just changing the names of the constants and changing the name of the charges, but it's the same thing. The only thing that changes, and that's what makes the gravitational field special, is the units. So let's take a look at the units of this thing. Now we know that the units of force are coulombs, are newtons, and the units of charge are coulombs. So let's take a look at the units of the electric field. So remember, this thing means units. So units of the electric field will be units of force divided by units of charge. So units of force are newtons, units of charge are coulomb. So these are the units of electric field. Is the number of newtons per coulomb that a charge will get, which makes sense. Now let's do this for the gravitational field. And in the same way, we have that the units of the gravitational field have to be equal to the units of force divided by the units of mass. The units of force are newtons, the units of mass are kilograms. Okay, so again, complete symmetry between this and this. It's just that the gravitational charge is mass and the electric charge is just charge. But if we know a little bit about units, we can actually rearrange this and we'll see what happens. So let's rearrange this thing. So then we have that the units of the gravitational field are newtons, but newtons are really kilograms meter times seconds to the minus 2, right? It's mass times acceleration. So divided by kilograms. And now what happens is that the kilograms cross out so that we get units of acceleration. And that's what makes the gravitational field so special, is that its units are units of acceleration. Whereas the units of the electric field are not units of acceleration. If I want to know the acceleration, I need to calculate the force and then divide by the mass. Whereas here, this already tells me the acceleration of a mass in here, because if I calculate the force and I divide by the mass, that is already the gravitational field. And the reason this happens is that the charge of the gravitational field is also the same thing that opposes its own motion. It's the inertial mass. It's the thing that makes it hard for something to change its movement. So the more it's attracted by a mass, the harder it is to actually accelerate it, so that the two effects compensate and we get plane acceleration for the gravitational field. But the basic idea that you should get is that this is symmetrical, this is symmetrical, this is symmetrical. If you know this, then you know this. Okay, so until now we've seen what we saw already in standard level, which were fields and forces. But now we need to start thinking about potential energy. Now, in order to understand potential energy, what I recommend is that you imagine that there is some kind of spring between the two charges or masses or whatever it is that you're analyzing, because that makes it much easier to understand. So for example, here I have two charges, and these charges are repelling each other. So one could imagine that, for example, there's a little spring connecting these two charges, and this spring is compressed so that if I let these two things go, this charge is going to just go this way forever. This one, let's just assume that it's not going to move because it's so heavy that it just stays put. So somehow this charge that has zero kinetic energy, because it was here, it was stuck, when I let it go, it was pushed by this charge and it gained more and more and more and more kinetic energy until it reached someplace really, really far away where this guy cannot push it anymore. And then all the potential energy that was in this little spring became the kinetic energy of this charge. Of course, this spring doesn't really exist. So what are we talking about when we talk about this little spring that between the two charges? And if you've been following this for long, you should probably think that it is the field. So really, when we talk about potential energy, we're talking about the potential energy stored in the field between two charges. So here we have this field that has a bunch of energy stored, and when I let these two charges go, this energy in the field, the potential energy, will become the kinetic energy of this particle here. Now, you may remember, but I'm just going to try to refresh your memory, how we actually calculated the potential energy of a spring. So in a spring what we did is we just made a graph of the force against the distance. And we had something like this, right? Because force equals kx. And what we said was like, okay, well, the potential energy stored in the spring is really the force that I have to do against the spring, well, the work that I have to do against the spring in order to separate the two pieces of the spring, or if I'm doing it this way, in order to bring them together, right? So here's my spring. Let's imagine that I want to move this charge this way. Then I need to do some kind of force against the spring, and therefore I need to do some work against the spring. And the further there I go, the more work that I need to do. And in order to calculate work, well, we know that work equals force times distance. But here we have a problem because the force keeps changing. It's getting bigger and bigger and bigger. So what we did was, well, no problem. What I can do is take a very small distance and calculate how much work I did. And I get this, well, kind of this little square here. And this will be the work that I had to do to move the spring from here at the beginning to here. And then I can say, well, okay, and how about move it a little more? And then it's like, well, then I will have to do this force now, times the distance. And I can keep doing this over and over and over. And for each little bit that I move the spring, I'm going to get the work. Of course, this is not very precise because the force is always changing, and I'm only using the force at these steps here. But what I can do is say, well, obviously what I'm doing is calculating the area under this curve. So what I do is forget about these little steps and just say that the work that I have to do is the area under this curve, which is this whole thing. And that's how we got the idea that the potential energy of a spring was 1/2 of kx squared, which was basically the height, which is kx, times the base, which is x, divided by 2 because this is a triangle. Now sometimes we want to do exactly this thing, that is calculate the area under a force displacement graph, but we can't do it so straightforwardly. And let me show you what I mean by that. So the basic idea is that if I want to calculate the potential energy stored in this system, I should do the same thing. Right? I should draw a force displacement graph, and then I should look at the area under this graph, and that's how I find out the potential energy stored. So if I do the same for two charges, what I have is that the force is k q q over r squared. So now let's plot this, and here's my force. And here's instead of x, I'm going to call it r, because this is really the distance from the center of one charge to the center of the other charge. Remember, r is not the radius, it's the distance between the centers of the charges. Okay, so how do we plot this? Well, I hope that you guys are getting better at this in math, but if you're not, the basic idea is that when r is very small, you have some number divided by something that's very, very small, so we can make many, many pieces. So this is very big. Actually, if I make r 0, then this is really, really, really big. Actually, it's infinitely big. So when r is very close to 0, the force is very, very big. It's infinite. Then as r becomes bigger, this becomes smaller. So I will get something like this. This will never be 0, because no matter how big r gets, this will always be positive. So I will have something that gets smaller and smaller and smaller as r becomes bigger. So let's just plot this, and I will have a graph like this. So now if I want to calculate the potential energy stored, I basically need to calculate an area under this curve. Which area? Well, in this case, I really want to see, okay, well, how much work do I need to do against this little spring in order to put these guys together? All the work that I did to put these guys together, that's the work, and therefore the energy that's stored in the spring, which remember is just the field. Okay, so therefore I need to imagine that at the beginning, these guys are infinitely separated. So this charge is infinitely far. If it's infinitely far, then the force is 0, and these two guys are happy. And then what I do is I start pushing this little charge in. So slowly push, push, push. And of course, the closer that I get, the harder it is to push, until I finally leave this charge here at a position that I'm going to call R0. So basically what I've done is I've pushed this charge Q between infinitely far and this position here, R0. So how much work have I done? Well, basically I've done the area between infinitely far and some point here that I will call R0. Let's put it here. Okay, so this area here is the work that I've done. Of course, this continues infinitely, though it's less and less important as we go further. So now I need to calculate this area, but I can't because this is not a triangle, just like here. This is a curve, and we don't know how to calculate areas of curves. Or do we? Now, hopefully, you now know how to calculate areas of curves, and you know that this area here is nothing but the integral between here and here of the force. If you don't know this, then what I'm going to do next is going to be very, very weird. I suggest you just skim over it and then come back when you actually do know how to do integrals. So let's calculate this. Then the potential energy is going to be equal to the work that I did, which is the integral between R0 and infinity of k q over r squared dr. And this basically means that I am integrating. This is dr just means that this is my integration variable. Just like in a derivative, dy dx means that I'm deriving with respect to dx. This just means that I'm integrating with respect to r, and that everything else is a constant. And what constants do is absolutely nothing. So I can ignore them and put them outside the integral sign. So let's do this. So I have potential energy then is just going to be equal to k, q, q. These three things are constant, they don't change, so I don't care about them. Integral between r0 and infinity of 1 over r squared dr. And remember that an integral is just the opposite of a derivative. So basically I need to find a function that when I derive it will give me this. In order to do this, I will do what I always do. I will express this as a negative exponent. Okay, so I got k, q, q, and then again the integral between r0 and infinity of r minus 2 dr. And just it's r minus 2 because remember that 1 over r to the n is just r to minus n. Okay, so now I can just do the integral. So it's k, q, Q, but I'm going to keep this in a bracket, but because I still need to replace the values at the extremes. Again, if you don't know what I'm doing, it means that you still haven't done definite integrals, just skim over this, look at the final formula, and come back here when you actually know how to integrate. Okay, so here I have this thing, and the integral of this, take my word for it, is r to the minus 1 over minus 1, which is the same thing as saying minus r to the minus 1, but I just wrote it like that so that you see where this is coming from. Between r0 and infinity. And now I just replace things. So actually, before I replace things, just to be nice, I'm going to make this look prettier and easier to understand. So this is minus 1 divided by r between r0 and infinity. And I really hope that you understood this step. Remember that 1 over minus 1 is the same as minus 1. And r to the minus 1 is the same as 1 over r. Okay, so let's continue. Then I have QQ, and what I need to do is evaluate this at infinity and then subtract this evaluated at r0. So minus 1 over r when r is infinity, so minus 1 over infinity, minus 1 over r0, which is, remember, the position at which the charge ends up. Now, 1 over infinity is just 0, because if I take a cake and I make infinite pieces, then the pieces are very, very small, actually infinitely small, which is 0. So this is 0, minus minus is plus, so I'm going to get minus minus 1 over r0. So basically I'm going to get k q over r0. And since I'm not integrating over r anymore, I can just forget that I called this r0 and call it r, which is basically any position that I want to put this thing. And this is the formula for the potential energy of a charge at a distance r from another one. So let's recapitulate. So we just found out that the potential energy of a charge q, small q, placed at a distance r from a bigger charge is kqq over r. Now, remembering what we know about gravity, let's try to figure out what the potential energy is going to look like for gravity. Well, let's see. The potential energy should be, of course, the gravitational constant. Now, what is the charge of gravity? Yes, it's the mass. So the big mass times the small mass divided by r. But there is a big difference, because here these two guys are positive, so they're repelling each other. So in order to bring this guy here from very far away, I actually need to do work. But in this case, if I put another mass here, they're not repelling each other, but they're actually attracting each other. So if I take this infinitely far away and I do nothing, it is going to come this way all on its own. So therefore, if I want to get this guy here in this position and for it to stay there, I actually have to do negative work. I need to work against it. I need to try to stop it. So in here, we need to put a negative sign in order to account for this fact. There's another way of seeing this, which is just, well, which sign would this have when the two charges were attracting each other? Well, one would be positive, the other one would be negative. So here we would have a minus sign. Because these guys are always attracting each other, there will always be a minus sign here. Good. So these are the formulas for electric and gravitational potential energy. Now, the next thing that we need to understand very well is the relationship between potential energy and force. So let's think for a moment. When we integrated, well, when we had the force, we needed to integrate with respect to r, and then we got the potential energy. So the next thing that we can ask ourselves is, if I have the potential energy, how can I get the force? Pause the video and tell me. Well, hopefully you thought, well, if in order to get the potential energy, I had to integrate the force, then in order to get the force, I would have to derive the potential energy. Let's see if that's true. So let's take the potential energy, And let's imagine that this is the force. Let's see if we get the right result. So the derivative of the potential energy with respect to r, and that's just kqqq, that's just a constant. So basically we're just deriving r to the minus 1, which will be minus r to the minus 2. That's the derivative of that. So we will get kqqq times r to the minus 2, which is over r squared, and then with a minus sign from the minus 1 of this guy that's deriving. So here's a minus. That didn't really work, right? Because we know that the force is positive, because these two guys are positive. So how do we fix this? Well, very simple. If I put a minus here, then this becomes a plus. So this is what we have just deduced, is that the electric force I can obtain by just deriving the potential energy of the charge at that point. Will this work for gravity? Well, let's see if this works for gravity. So let's take force equals minus the derivative of the potential energy with respect to r, and again I'm going to get the same. R to the minus 1 will become an r to the minus 2 with a negative, so this negative will disappear. But here we need to be careful. So we have, when I derive, this will get an extra negative that will disappear with this negative, so that's positive, but then I will still keep this negative here. So there's still one negative, so I will have minus gmm over r squared. And now you may say, no, that can't be, because the gravitational force does not have a negative sign. But actually it does. The gravitational force is always attractive, so it really does have a negative sign. What happens is that we normally talk about the magnitude of the gravitational force, and the magnitude cannot be negative, so we just ignore this negative sign. But if we think about the force as a vector, and this as like a 1D vector, this is telling us that the force is pointing into the other mass this way. So indeed, we recover the force in both cases, which is really cool. So let's recapitulate. If I want to get the potential energy, I integrate the force with a negative sign. If I want to get the force, I derive the potential energy. So therefore, the force is nothing but the slope of the potential energy. And the potential energy is nothing but the area of the force displacement graph. This is actually a really important result, because nowadays, in modern physics, we don't even use forces anymore. Why would we? If you know the energy, you know the force. The energy is all you need. So if we want to describe a system, we just use energy. And all the laws that we can express, they just refer to energy, and forces are a bit of an outdated concept nowadays. So after all this work, we finally are in a position to talk about potential. And I hope you remember something about potential before when we did electricity, and we said something like, it's the work per unit charge that we need to do to put a charge in a certain place. Well, now we can understand potential much better using the notion of potential energy. So basically, the potential of something is just the potential energy per unit charge, and the potential difference is just the potential energy difference per unit charge. So, for example, if I put a charge here and there's 4 joules stored in the field, I may want to know, okay, yeah, but what if this charge was half of that? Well, there would be 2 joules stored in the field. Okay, what if I don't know the charge? Then I would be like, well, maybe you have 10 joules for every coulomb that you put in the field. And we call these joules per coulomb faults. So the basic idea is that potential just tells me how many joules will the field store per unit of charge that I put in there. And we assume that this charge here is fixed, doesn't move, it's just stuck with a needle to the ground. Okay. Now the calculation is actually really easy, right? So if I have this is my potential energy, and I want to know what the potential energy is per unit charge, all I need to do is divide by the charge. Which of these charges? Well, the one that I'm changing. Since this one is stuck here and does not change, this is the one that I have to divide by. Okay, so let's do this. Now let's call the potential V, and it's just the potential energy per unit charge, little charge, and it's just K, Q, Q over R, and then divided over Q. Remember that dividing is the same as multiplying by the inverse, so I'm multiplying this thing by 1 over Q, so therefore the potential is just KQ over R. And that's it. So this is the potential of that a spherical charge will create at a point R. Easy as that. Now let's do the same with gravity. And again, the gravitational potential is just like this potential, but we need to figure out how much energy is stored, not per unit charge, but per unit of gravitational charge. And remember that the gravitational charge is the mass. Now before I move on, there is a mistake here. Let's see if you can see it. Pause the video and think about it for a moment. Well, hopefully you saw that there's a minus sign missing here. If you didn't, then you just need to remember that the energy that this charge has here cannot be positive, because this charge is trapped. Basically, if I let it go, it will just go into here and never come out. If for this charge to have zero energy, which means to just be like a regular billiard ball, free to go about its business, or like a little ball in the middle of empty space that's not being trapped by any planet, this would have to have an energy of 0 at least. And then more than 0 energy, it would just, be going very fast, whoever knows where. So the basic idea is that for any mass or charge that is trapped in an orbit, the energy has to be negative, because I need to do work to get it out of there. Anyway, so here's my potential energy, and my gravitational potential energy will be the potential energy per unit of mass. And again, the little mass, because this one I'm assuming that it's just there, cannot be moved, cannot be changed. Okay, so let's do it. So V will be equal to EP over M, and I'm not even going to do this, you just figure this out yourself. You get minus GM over R. And there you go. So again, we have exactly the same expression here and here. The only difference is that this gets a minus sign because this is always attractive. So if you had a minus charge here, this would also be negative. It's just that here the minus is absorbed into the charge. And now that we have this here, we can ask ourselves, okay, so what is the relationship between this thing and the field? Right? Because the field, let's see if we remember this. So the field was equal, the electric field is just KQ over R squared, right? So do you see that just like, so when I had the force, I integrate and I get the potential energy. And here, the field is nothing but the force per unit charge, right? So the force divided by charge. And then the potential energy, and then the potential is nothing but the potential energy per unit charge. So this divided by the charge. So basically I'm doing the same thing here. So I can ask myself, what would happen if I integrated the field? What would I get? So pause the video and tell me. Well, hopefully you figured out, since this is just the force per unit charge, and this is just the potential energy per unit charge, basically all I need to do is just integrate the field, and I'm going to get the potential. And what happens if I derive the potential? Well, I'm going to get the field. So the basic idea then is that the field, and again remember there's a minus sign, is minus the derivative of the potential. So if I have, for example, a certain potential like this, and I want to know the field at this point, let's say here, for example, then all I need to do is look at the slope. See, so for example here, I can see that the field has to be very, very small, because the slope of this is very small also. And this makes sense, because if the slope is very small, it means that there's no energy difference between here and here. So why would a charge want to go between here and here? This is like being in a flat surface. There's no potential energy difference, so why would your ball move? Now, between here and here, there has to be a humongous field, right? So here at this point, this has to be a huge field. Well, because there's a huge energy difference here. So of course the particle will like to go from the higher energy to the lower energy. Another way of thinking about this is like there's a cliff, right? So on top of the cliff there's lots of energy. At the bottom of the cliff there's very little energy. And what happens when you go and stand on top of the cliff but a little bit further? Then you just go down, right? So it's the same idea. The faster that the potential decreases, the more field we're going to have at that point. If the potential is always the same, then there's no reason for charges to move anywhere. So they won't move anywhere. So then this means that they feel no force. This means that the field is zero. Don't worry if this looks a little bit abstract for you now. We will go over this over and over in class, and we will try to practice this more. Anyway, we can do exactly the same for the gravitational potential, because remember that the field is just the force per unit mass, and the potential is just the potential energy per unit mass. So again, if I want to get the gravitational potential from the field, I just integrate. If I want to get the field from the gravitational potential, I just derive, just like I did here. So in the same way, G is just minus dV dr. Okay, so unfortunately we didn't finish everything that I wanted to do in this video, but I think we will just do the rest in class because I don't want to overwhelm you. This is what you should really have understood from this video. So the first idea is that each field has its charge. In the case of the electric field, we just call it charge, but in the case of the gravitational field, we call it mass. But it behaves exactly the same way. So if you understand how the electric field works, you understand how the gravitational field works. They're exactly the same thing. The only difference is that mass cannot be negative, whereas electric charge can. Now, the next thing that you should understand is that potential energy is the energy that's stored in the field. And by that we mean that really you can imagine the field like some kind of spring, and then when I put two masses together, it's in this spring that the energy is stored. And this will allow you to make sure that you understand that that's all the energy that's stored. It's not per unit of, it's not per charge. If I have two charges, they don't all have that potential energy and then another one, but it's just the whole system that has this energy. Now, this is also very important. If you have a force displacement graph, you can calculate the potential energy by taking the integral. However, this is tricky because there's negative signs and things like that. The safest thing is to think in physical terms. What do I need to get? What does it make sense to have? Should this be negative or positive? And then choose the sign at the very end, just by understanding the physics of the problem, not by just mindlessly applying a formula. Finally, the idea that potential is potential energy per unit charge, something that you should know already, but that it's essential, and that I will just drill over and over again. And finally, this idea that when you derive the potential, you get the field. And what you need to understand is, well, if the potential changes very quickly, it means that there's a very strong field. If the potential almost does not change, then there's no reason for the charges to move. Therefore, there's hardly any field, which is, remember, what pushes charges in the first place.